October 26th. Rainy day today, still misting, warming up a bit. Crickets are singing. Build your own greenhouse, part 4, thermal management. October 26th, 2020. Here we are in the greenhouse again. So, came in to start up the stove tonight. Saw one of the thermal circulator pumps that I had hung up here hanging. Kind of inspired me. Why not just hook it up for test mode? So, using the existing coil and hoses that are there, I unscrewed the adapter off the old pump, put it on the new pump, dropped it in, and away we go. So I just ran a few tests just to make sure it works. It does. And so I took my script over here and did some modifications to it. Just a simplified version, basically, without going into a lot of detail. I had previously had it set up so that it would gear thermal mass management of this thermal mass on top of the stove versus this one and what is usually the large tank here. It would gear how it manages the heat in those based on what the outside temperature is. So I think it was like set at like below 15 degrees. It would start raising the temperature that it held this at before it tapped heat off it. So if, say, before I was tapping heat off when it hit 130 and then shutting the pump off when it hit 120, you know, the temperature dropping as the heat pump takes heat off to one of the thermal mass banks and the theoretical bank that was here before. Maybe I'll throw a clip in of the 275 gallon water tote that was here. Anyway, you know, if ordinarily I would turn the pump on at 130, back off at 120, when it was 15 degrees or colder out, I would leave that and go, I would only bring the pump on at 140 and turn off at 130, and in that way we're actually radiating more heat because we have a higher difference in temperature between this thermal mass and the air temperature in the greenhouse, so you can radiate more heat faster as a way to help compensate against the extreme cold that's outside. I hope I've explained that in a way that you can understand. Anyway, so instead of that script, which normally manages this on a more complex level, I've just got it set up to kick on at anything over 120 and kick off at 120 or below, just for some testing. I ordinarily prefer closed tanks, closed top tanks, for a few reasons. One, open top tanks, you get a tremendous amount of evaporation, especially in very cold weather when the air conditions are very dry, and then of course in here, because we're dealing with relative humidity, it's even drier. I mentioned in previous videos I do actually wet the floor of the greenhouse down in the wintertime usually to maintain a good humidity in here. And in fact, even tonight, even though it's raining, misty, and damp out, I probably will come through and put some water down because it's a little bit dry in here. Don't have the humidity sensor rigged up again yet. I think I'm just going to replace that. I tried to get that working before, but it seems like that sensor got struck by the lightning as well. So we'll get back to that. Let's see. So anyway, basically I'm just going to do a quick test here, just show you how the pump works. Basically the pump is on the bottom. It's came in today, so I'm excited about that. They're rated at 800 liters per hour. Let's see, that'd be 200 gallons an hour, so under a gallon a minute. Just a submersible pump. I showed it in a previous video. I took to this was effectively a garden hose. It's actually a hot water washer hose. That goes into here, goes into the coil inside of here, which I'll just show you briefly. That is a wort cooling coil there, basically for cooling beer wort. When you make beer, you boil it and you put all the ingredients together, and then you cool it before you pitch yeast into it. If you pitch yeast into it too early, it ferments too fast, it doesn't come out well. Anyway, so this is a wort cooler, and then it comes back into this hose, which is set up to take a garden hose adapter. That makes it so I can switch things out. I can even hook up to a hose and spray hot water if I need to around here. Another adaptation that I use of that in the winter is I have a rain shower head here, and so I can come out here when I'm flowing the nice spring water again. So I've used a rain shower head here, which I gotta tell you, if you've never showered under a rain shower head, you're missing out on one of the best luxuries of life. So I just thought I'd show it. The spring water, I can actually take a nice hot shower out here if I need to. So if power goes down, I can take a hot shower from wood heat and solar power. And that is a really handy, nice option to have, let me say. It's also a great environment to take a shower in. It felt a little weird at first, you know, I'm used to being in a shower stall, but man, once I got used to it, it was like, wow, it was really cool being right next to plants. And cozy in a greenhouse when it's, you know, 10 degrees and icy. Anyway, I've been babbling on a bit here, and we're going to go ahead and get this test started. Sorry this video is going to end up being a long one, but at a lot of detail I want to relate. Okay, so I'm going to go ahead and activate the script here, and I'll let you have a look at the wattage here. I'll shut the audio amplifier off, and we'll take a look at our current wattage consumption at 10.17 watts, just about 10 watts. And then we're going to go ahead and bring this script on, which will bring the pump on. Okay, you can see we've exceeded our temperature limit of 120 with the hot average, or H3. Currently is 24,429 BTUs in the big thermal mass tank on top of the stove. Outside temperature is 50 degrees. Stove temp is reading 86. And the pump is on and running. Wattage is up at 17.65 now. So it looks like that pump draws about 8 or 9 watts as well. So that's good. And then we'll just come over here, and you can see this water is actually moving, and you can see steam rising off of it because it's hot water coming back out of this hose. And you can see steam rising right off of that. That water is about, it's probably 105, might be 110. And of course it's only been circulating for a minute. It'll probably warm up a bit as the hose and the coil and everything start to stabilize and heat transfer. So now we are pumping heat basically out of this into this tank. I may incorporate this open tank system a little bit more this year as a means of evaporating moisture into the greenhouse to help maintain humidity levels. I think I could actually drive that off of the humidity sensor and then you know, detect where humidity is at. If it's too low, we could pick up some of the heat off of this into probably a smaller tank than this big one. And then we could put like a float valve coming into that with a water supply to keep it topped up, and then use that tank basically as a way to diffuse humidity into the greenhouse on an automatic level and controlled by a computer or Arduino or some sort of microcontroller process. Right now I'm running Raspberry Pi for everything. I don't know, I did have a question from my friend Brad over at Grow the Farm Up about if I built this board myself or not. I did not. This is a Raspberry Pi 4. This is actually two boards here, and I've got the fried pie right here for you to check out. So this is a Raspberry Pi 4 here that I'm holding, and it's an ARM-based processor, pretty fast. I forget what the actual processor speed is, but it's a 4-core processor. Has a 1 gigabit internet connection or Ethernet connection on it, 2 USB 3.0 ports, and 2 USB 1 or 2.0 ports. This is a really robust little processor. Actually, I'm able to watch YouTube videos on here while I do stuff. I've even tested it for editing. It's not even all that bad for editing video. I was pretty surprised and impressed with it. And of course, that was when I first got it. This Pi has, like the firmware and software since this was released has been updated tremendously. So it's much more stable and much more capable now. Once they've had a chance to roll it out and see how the hardware performs, you can kind of extend out into the limits of what the hardware can actually handle. So it's been stabilized better. It actually can be set up for a USB boot off of like a solid state hard drive. Typically these are run off of these little 32-bit micro SD cards. You can see the one that's in there. That's where the operating system and database and all that stuff is right now. In the future, I plan to go out to basically RAID a pair of solid state hard drives set up in some sort of RAID configuration to have redundancy, both for the database and the operating system. And also those solid state drives are a little bit faster than most of these chips unless you pay a lot of money for one of these micro SD chips. The other thing is these are only good for so many reads or writes, so after a while you burn out a chip. I'm reading and writing at least once a minute because my database is logging every single minute of every single day. And so I find I go through a chip like this in about a year and a half with all those read writes. So the solid state drive is definitely a solution better than that. So on top of this Raspberry Pi is something called the Pi Easy Connect. This is basically just a board so you can hook in screw terminals and resistors and all of those like external components you need to pick up one-wire networks or go out to relays. So this is the best one that I could find. It's pretty good. I don't have a whole lot of complaints about it. So into this is connected all of my sensor networks. This Ethernet looking cable right here with only 3 wires coming in is the feed that goes out to all those one-wire digital sensors. Those are Dallas Instruments DS18B20 sensors, and so they all are rigged together on the same wire. This one over here on the left, these 3 wires going out go to the Adafruit DHT22 humidity sensor, which, where is it? There it is. That's this little guy right here. I think that's the one that's fried. I'll be replacing that. These are about $10 a piece. They're expensive. Those DS18B20 one-wire thermal sensors are only about $2 a piece, maybe a little bit more. These, I should also mention, these also do temperature as well. Haven't found these to be super reliable as far as stability of readings. We did a lot of messing around with code to delay and check and recheck our readings before logging them to the database, and we still get errors out of these things. That may change when I replace this with a new one. Ultimately, I probably will not continue to use that sensor. I'll probably use something different. I might use an analog type sensor once we switch over to Arduino, because we'll have the analog to digital conversion interface on board to do that. Raspberry Pi does not come with analog to digital conversion on board. So you kind of have to either build your own circuitry for it, or find a way to integrate it. Anyway, the Pi Easy Connect runs that. This is just a cooling fan for it. I got new heat sinks on the way for the new Pi. I tried to pull these off, but they're they're not going to stick on again and be good heat sinks. So new ones on the way for this. This is running without heat sinks right now. I'm just not putting a lot of processor load on it. And then let's see, these other 8 wires at the bottom are the ones going out through this Ethernet cable, the ones that do the 8 relay board up here, and that's where we're controlling everything, venting, pumps, all those remote controls are run through that relay board, and those basically each correlate to GPIO pins coming off of this 40-pin header on the Raspberry Pi. So I hope that I've explained the basics of this and how it works all together. The other cool thing about this is it supports dual monitors. So you could have a dual like a monitor here, and then I just have one that I sit here, so when I'm sitting in front of the stove, I can see it more clearly. But you could hook to like a projector or something, have a projector screen up and be able to watch videos or movies or whatever while you're working, or whatever. Anyway, it's really nice. It does lots of functions. In the future, the Raspberry Pi, at least for now, is going to stay as my main server processor for stuff. But we're going to move over to Arduino, something Arduino based, or something based on the chip that goes in the Arduino, to manage all the controls, mostly just for reliability reasons. And then we'll pull from that probably over I2C or serial interface, and pull the data from the Arduino to the database. And ultimately this will end up managing farm-wide stuff, but we'll get into the technical details of that another time. I just want to share what the Raspberry Pi 4 is for my friend Brad, because he was not familiar with it. So this Raspberry Pi 4 is about 80 bucks. This one I have is the 4 GB RAM version. So not a bad price for everything it can do, and the speed of the processor and the speed of the architecture. Both the USB 3.0 and the 1 gigabit Ethernet are new additions on the Pi 4 only. Before that we were stuck down at 100 megabit per second and USB 2.0, I think, on the Pi 3. Anyway, that's that. This pump has been transferring. Let's go take a look at that. Oh, and before we do, let's just have a look at where things are at. Oh yeah, we're down to 21,919 BTUs in the thermal mass on the stove, or 125 degrees Fahrenheit. So we're quickly closing on the trip off here. Pretty amazing how fast it can transfer that heat. Let's go take a look at the tank. Alright, here we are. I still have to dig up a couple of new working sensors to go in this thermal mass tank. There usually is a pair of sensors in here, a high sensor and a low sensor. That way, because of water stratification, you don't get inaccurate readings about what your tank temperature is. So when I calculate BTUs in most of my thermal masses, and I usually would have a high and low in this also, I use a high sensor and a low sensor, and I average those two together, and then that's what I calculate my total BTUs of storage based on, so that I have an accurate representation of what my actual heat value in storage is. So calculating BTUs for storage is really simple. And 1 gallon of water is 8.33 pounds. So for every 1 degree Fahrenheit you raise or lower, you've gained 8.33 BTUs per gallon of water. So that's how that works. And at one of my other videos I did the math on that, so maybe I can find that video and throw a link for you. But anyway, so this is warm. Wow, I'd say that's like probably 90 on top, and the tip of my finger is about the stratification point, maybe a little higher up. About 6 inches down it drops down to probably 60, 65 degrees maybe. So we've transferred a pretty good amount of water, and we'll continue to monitor this and see how it does. So I guess I'll just mention real quick, The stove was kind of slacking here. I put some fairly green wood on here. So it was running a little bit slow, and so we were actually pulling BTUs off of here and not recovering them very fast. So I've opened the door here to let a little airflow in and give this a little stokey stoke, and then you can hear that draft pick up and the fire go and the stove creak as it heats up. And I just want to show you here, I killed this pump just a minute ago here, but I want to show, if we look back, the hot average is now at 121.1, and if we go back a few rounds here, you can see it was at 124, right? And BTUs were at 21,545, and then now down here, BTUs in storage were at 2346. So it's been falling with the pump on. I killed the script, so the pump is still on. So I'm going to bring the script back online and let it continue piping heat off, but we're going to see if we can keep up with it now, with the stove running throttled open a little bit more and producing more heat. Usually when I have this running really hot, I can actually almost keep up with the heat pump. When we're pumping heat to a cold tank off of a relatively cool thermal mass tank, like say 120, 130 degrees, I can basically capture most of the heat that's coming off the top of the stove. And that goes back to delta T. We'll talk about that when we get deeper into the greenhouse series. I'll just give you a shot here now that we've been pumping for a bit, and you saw how many BTUs we were taking off of the thermal mass. I think we started at what, 25,000, and now we're down close to 20,000, in that range. I think that's correct. We might have been at 27,000. Anyway, you can see now that we've transferred quite a bit of heat in here, you see all the steam and fog coming off of here. This is why open top tanks can be a negative benefit, because you could end up putting all sorts of moisture in the greenhouse that you don't want if you have a humidity problem, which can happen. So so this is why a closed tank is so much better, because you're not letting all your moisture evaporate off. Of course, I should mention, in the process of evaporating off moisture, you're also dumping a lot of heat. So you can use this to your advantage or use it against you. In evaporating moisture off and dumping heat, if it's really cold weather out, that's a great way to A, keep humidity, and B, to actually transfer more heat into the air and to keep the air temperature higher. The more humidity you have in the air, the better that air holds temperature, because again, it goes back to the thermal mass storage qualities of water. Even when water is in a very small droplet form in the air, it still acts the same way. It still retains the same amount of heat, and that has a huge effect on how much heat is actually in the air. You'd be amazed what the feel difference is like when you come in the greenhouse and the humidity is low and it's warm in here. You can still feel cold, but when you come in here and the humidity is high, boy, it hits you like a hot summer day. It's an amazing difference that you can feel as a living being. Anyway, I just wanted to go into that a little bit and show the evaporation effect here. And so this also kind of gives you an idea of how much moisture is being evaporated off. And that relay that just clicked, and I'm sure you saw the hose jump, that means our pump just went off. Yeah, see? It was off for a minute there, and now it's back on. And so that shows you that we're still producing heat. Very interesting. Oh, sorry about the headlight. And notice that hot average temp is climbing. 120, 120.2. 120.2 again. but that's how fast you can start producing heat with the stove. And it shows just how responsive that really is. And also look at our stove temperature. We were at 80 something before when I first started this video, and now we're showing 93 and a half. And again, I'll just mention for those who might not have seen other videos, that stove temperature sensor is this sensor right here next to the stove. It's a $2 DS18B20 sensor. You can buy digital sensors for high temperatures for stoves, but they start around $100 and they can go up from there. And since I don't need to know the exact hearth temperature of the stove, this is a simple way to figure out what the stove is doing without spending a tremendous amount of money to find that out. Basically all we're doing is picking up radiated heat off the edge of the stove, off the side of the stove, on the sensor, and you'd be surprised how responsive this is. You can actually see when little different pieces of wood, like when you got this stoked up good and there's a few different pieces bridged up, and one falls down and the burn slows down, you can see that within, you know, a minute or two on the chart. So very simple way to have a sensitive temperature sensor of what the stove is doing without spending a lot of money to do it. And of course, you know, if you buy one of those expensive sensors and it goes bad, you're at another $100 to replace it. That can add up really quick. Yeah. Anyway, I think that covers most of what I wanted to talk about tonight. And this is going to be a really long video, and I apologize for that, but I feel it's pertinent and important information.